Okay, let's get started. We are now in day number 2 of weekend number 1. And on the agenda today, I'm going to start in with a little bit of lecture stuff while everybody's waking up and getting logged in. And while you're doing that, you're bored, you can go ahead and go ahead and download the examples from yesterday if you couldn't get them working. I also changed around the second one a little bit, and I'll talk about that when we get ready to switch on after some boring PowerPoint stuff. So I put them out on the website. I know I said I wasn't going to do it, but I decided it was probably worth doing anyway. And I also linked them to the YouTube videos, so they're in multiple places right now. So if you go into summer 2013 and you go into object-oriented programming with C++ and you go down to the examples, miscellaneous examples is where they're located. So MISC, miscellaneous examples. And in here you'll see on the bottom it says lecture number 1, source code example. That was the first lecture in the morning. This is really lecture number 2, which I did yesterday in the afternoon. And then this morning will be lecture number 3, and then in the afternoon we have lecture number 4. So I'm breaking out the morning, afternoon into two kind of separate lecture example sets. So this one will give you the .c++ file that was non-object oriented. It will give you the person A and the structure and the class and all the goodies that went along with that example. And then this one down here is the source code with all of the files, and it's a zipped file because it has multiple files that are included together. And those files are the example I built with the person and the dog. I made some changes to it this morning. I made some adjustments, and I'm going to go over the adjustments. So this is a little bit more up to date than the lecture right now. But in any case, we'll definitely surpass that and move forward. But I kind of cleaned it up a little bit, put a few more comments in it, changed some of the data types. But I'll explain that when we go over that again. So if you're bored and you're looking for something to do, go ahead and download both of those two if you don't have them working from yesterday. And then I'll do the same for today as well. So you'll have working examples. Just in case you can't type fast enough, you miss something, you have a typo, something's not working for you, you can see what went wrong, hopefully. Alright, so I'm going to give you, this is lecture number 2. And I'm going to talk about a few concepts, and then we'll go do some source code, and then we'll have lunch, and then we'll come back, do some more concepts, do some more source code, and then we'll call it a weekend, which is the game plan for today. Today's lunch will probably be more like an hour, hour and a half instead of 2 hours. It was a little too long yesterday. So I mean, hopefully if we fly through this stuff, depending upon how the day goes, we'll get out at about 5:30, just like yesterday. And then I also hang around, and I hung around yesterday till actually about 6:45 to help people troubleshoot problems and stuff. So if you do have a problem, don't worry about it. There'll be some time at the end of the day. I usually hang around at least for about an hour after the class ends. And I actually had about 3 people troubleshooted their assignment number 1, and 2 of them turned it in already. So if you need help with the assignments, you have a bug, you have something that's not going right, just wait. And then towards the end of the day, I do have like about an hour left. I'm going to call it office hours at the end of the day there. So don't hurry out completely, and you'll be able to get some extra help if you need it. So we don't actually have tutors at I2 for this, although there's talk about it happening in the future. But we'll see what happens. So this is lecture number 2. It's on data types and data abstraction. And what I want to cover now is, because we're looking at data types in terms of those classes and the structures, I want to look at the concept of the namespaces, how to create a namespace, the built-in data types themselves, literal constants, variables. We're going to start pointers, but we probably won't start pointers till after lunch. We'll see how far we get. But pointers is also another topic for today. And then references, because we need pointers to reference objects. We probably will touch a little bit upon inheritance, but probably not too much overloading and overriding. So I'll show you inheritance towards the end of the day after lunch. So, which is a lot to cover on our first weekend, so it's we're doing okay. So what is this using namespace? A lot of people have asked me. I've answered a lot of people, so I figured it merits a little bit of explanation as well from a formal perspective. And then let me show you how to make one. It's actually pretty easy. So we have this blue using namespace from day 1. We've been looking at that, and everyone has been, kind of taking it, as face value for what it is. And I keep telling you it's an environment kind of thing, you know, where it's defining the environment. Well, here's the problem. When you have two variables or functions in the global scope that have the same name, when you compile it, you're going to get an error because you have a name conflict. You can't have two CNs, two COUTs as an example, or FN, or I don't know, whatever name you're going to use for your variables, for your methods, for your classes, they can't match. So when you use third-party libraries, you generally are getting things that are going to match, and there's no control over it because you're not writing it, somebody else is writing it. Also, when you're using classes that the rest of your team members in your development team are using or creating, you don't know what they're going to use either. So if you can't control it, what you do is you make a namespace to avoid the collisions, and then you just load the duplicate name series in different namespaces, and you switch back and forth when you want to use this one, when you want to use that one, and it allows you a little bit more flexibility, and it resolves the name collision. So to avoid the name collision, you're going to use a unique identifier of its own. So in C, you use multiple third-party libraries, there's name collision, and you have choices. Here's your choices. You can get the source code to the libraries and modify and recompile it, change all the names. Not such a good idea. Ask the library publisher to rename their identifiers, not such a good thing either. Or decide not to use one of the libraries. That defeats the purpose of using it. So none of the above options are available. Then we have namespaces. So that's where this namespace is coming into place. And Dev just uses them by default. Other compilers don't require them. Dev requires the namespace. It actually creates namespace std that puts in there identifiers. So the problem yesterday with my string was I wasn't including the namespace in the files that I was supposed to be using, that I was using the string in, and I need to put that in there, otherwise it can't find string. And the string that I was trying to use was the one that was defined by the compiler, which has the lowercase s. There's another string library that I use often that has an uppercase s. Same name, but it's actually two different names because of the lowercase and uppercase. It's case sensitive. So long story short, the namespace was the problem, which is why the string wasn't working. So I fixed that in the example, and I'll show it to you when I move over to the source code. But anyway, so here we have the identifiers. We're declaring them within a block that are associated with the block's namespace identifier. And then all the references to the identifiers from the outside block must indicate the namespace identifier if we're going to do it this way. And one example of the namespace is the standard C++ libraries and identifiers such as cout and the stream object. So this example here is showing you std, and then we have the 2 colons cout. Another thing I wanted to show you, somebody else did this yesterday with string. You put the word string here, you put 2 semicolons, and you go string, because string is inside a string. So you don't necessarily have to do that. In fact, you don't have to do this at all if you include the namespace. So you can access objects inside of the namespace directly, or you can do them automatically. So sometimes you see the syntax because people learned how to do it one way and they didn't realize they don't need to do it like that. You can just include using namespace. So if you define namespace standard, you can use the scope resolution operator, which is the 2 colons together. And here we have our scope resolution operator. That's tedious. Although I see people doing it all the time, it's kind of tedious. Every time you're going to write cout, you're going to go std : cout. And then you have to do it for every time you use cout, every time you use cn, and every time you use anything in the standard libraries, which can be kind of tedious. So you do this instead, using namespace. And you specify which namespace you're going to use, using namespace std. Then down here, you don't have to put std : cout or cn. So it takes it makes your life easier because you don't have to keep specifying where it's from. You just say, hey, just use this namespace, and then inside the namespace, we're going to have all of these names of all these literal constants and stuff, and these functions and methods and everything. So you admit the corresponding namespace reference down here, and then now you just say using namespace std. So that's the namespace mystery that we saw yesterday. And then you might be wondering, well, how do we create our own? You can create your own namespace. You don't have to use the standard one, although I don't recommend doing it unless you have a third-party library or something and you need to do this. It's kind of tedious. So here's how you define your own. You say, and what does this look like? It looks like a structure, it looks like a class, looks like looks like all of the other user-defined user-defined complex data types that we've looked at yesterday. It's the same format, but instead of saying class up here or structure right here, we say namespace. So here's namespace my names, and inside of my names we have value 1, we have value 2, and we have a method, and the method's called compute sum. So inside of std we've got all the data that we're going to use, and then we have one that says cin, cout, all of the other IOStream functions or methods that belong to that namespace. And then in our compute sum we have return value 1 plus value 2. And so what we've done in here is we've defined the namespace by calling it a namespace. We gave it a name. We put all of our data members and all of our member functions in there. Looks like a class actually. Looks like a class without a header file, if anything. And then in main we can do this, or we can just say using my names and using std. We can use both of them. So here we can go my names with the 2 semicolons there and preface that, well, compute sum is inside of here, and this is my names, and then std : cout, and then std : See how it gets tedious, which is why you don't want to do it this way. Every time you're going to use a method or a variable or something, you have to preface where it came from, which is kind of tedious. So, or you can just say using namespace. So here we go. We got the namespace defined over here. This is the example we saw on the previous slide. So if you use multiple namespace statements, you may get a compiler error due to ambiguity if you have the same thing in multiple namespaces. But if your namespaces have different items in there, we have, as an example over here, namespace my names, namespace my other names. And then up here I'm going to use using namespace std, using namespace my names, using namespace my other names. So, and then in here I'm going to say value 1 is equal to 50. You're like, where would value 1 come from? It's over here. But which value 1 is it? Is it value 1 from my names or my other names? Kind of ambiguous. That's the problem you run into if you create your own namespaces, put a bunch of methods in there, put a bunch of data in there, and then just start using multiples together. So most people will stick with this one here. In here we've defined things like cin, cout, and the string and everything else is in there. So, and then we include the using namespace standard, and we're all happy. If you're going to do this, you might as well create a class for it and use an object and actually do it. So this is not a substitute for object-oriented programming or for environment variables or anything like that. It's just a way of organizing the environments for which you're going to have name resolution. So if you're looking for a particular method and it says use this method, where'd it come from? So it came from here. It came from one of our namespaces. So in dev and in some other compilers, the standard namespace includes the source code for iostream.h, string.h, and a bunch of other commonly used standard libraries, standard interface libraries. So that's where the namespace is coming from. So you can also define nested namespaces. You can put a namespace inside of a namespace. I don't see anyone ever doing that. I don't see anyone ever doing this either, but it does come in handy if you have third-party libraries and you don't want to tell the developer to change the names of everything. Then this is your solution. So here we have namespace my inner names, which is inside of namespace my names. So we have that going on there. So what do we got here? My names, and then we have double resolution here. My names, my inner names, value 3. Value 3 is inside of my inner names, which is inside of my names. So that's kind of confusing if you ask me. So numerical data types. Alright, so as I was pointed out, I didn't even realize yesterday when I was writing that example that I was using integers for everything. And then it wasn't until after class that somebody told me, you told me that why is it just integers? And I started thinking about it. I'm like, oh, that's why I changed the example last night actually. It was because I'm thinking, oh, that's kind of interesting. I didn't realize I was doing that. And it's one of the things that happens when you just write stuff on the fly. Well, it happens to me all the time. But there are other data types out there outside of integers. The character, the short, the long, the double, the float, all of them can be used inside of classes. So when we go back out to the source code example that I started with yesterday, I actually created more data types in there. and I finished, and I'll show you so I don't have to type it. I finished one or two of the, well, in the dog, I believe. One of them, we'll write the other ones. I finished the implementation of the constructors, and so you can see how that works as well. And we'll get to that in a few minutes. But I wanted to show you that we do have other data types, and they do take up different lengths in memory. And the common here is the float or the double. I usually use a float instead because it's a little bit more efficient. And then we have the long double. It represents a float value, 1 machine word plus 2 machine words or 3 or 4 machine words. So it does, by default, the double's a long double, takes up more memory than the float. They're both going to show precision. And then we have the short, the integer, and the long that we can put in there as well. So in terms of the numerical data types here, the characters, here as an example, the value of an 8-bit unsigned character ranges from 0 to 255, while the range of an 8-bit signed character runs from -128 to 127. So we're getting a fuller range of values. What does that mean? It means the value that you're able to assign to the data type is specific about which data type you're using, which is one thing that usually trips up brand new programmers. If you've programmed in another language, you're familiar with the concept of the data type. You're just naming the storage. But I thought because I'm going to talk about pointers today, I thought I'd talk about data types just to refresh your memory on the concept. So you're actually just specifying the size of the space that you're reserving, along with the allowable operations that can be performed on that space that you've got. The interesting thing with literals is that we can create what's called the literal constants. These are just variables that don't change. We don't necessarily have to define them, we can just declare them. So here we have students equals 21, double pi, we've got the 3.14. We've got, just kind of, values that aren't going to change, but we refer to them as literal constants. We can put them anywhere we want, which is kind of different from like a data member of a class. Talk about classes. So just think that the concept exists. We can also do, and we use prefixes to write the literal integer constants in decimal, octal, or hexadecimal notation. You'll never do this. You'll never have a need to do this, actually. But no decimal, no prefix for a decimal, :15 as an example. Or here we have 0.015, which is equal to 13 decimal. So we can change the values around. The reason why I'm showing this is because we want to look at this here. In language programming, how do we know that this is a float? Well, we can put the character F next to it. Or we can just give it a value that's equivalent to it. So if I have a float as an example and I'm only using 1 and it's 1.0, I actually have to type in 1.0 when I assign it. If I type in 1, I have to use an F right next to it. If I put an F right next to it, it says, I'll convert it to a float. You're basically specifying that this is a float value when you put a little f next to it. So by default, the C++ compiler assumes that all literal integers constants are of type int and that all literal float constants are of type double. So there's an assumption that goes on. In the example I'm going to show you, I'm not going to use this technique because I'm going to put decimal points in there when I give it the value. You can specify different types by appending a letter to the integral constant. So we have U for unsigned, L for long, unsigned long, float. This is the one you're going to use more often because it's going to want a float, but you're going to give it an integer because there's no decimal precision. But it's still stored as a float. And then the compiler's going to say, well, I'm converting an integer to a float. And usually it's a warning message these days. You don't like the warning message, put a little f at the end of it. At the end of the number, just put an f on the end of the number. And then what ends up happening, and in fact this is the syntax right here, and what ends up happening, or convert it to float. Use float like this, actually, inside of the opening and closing brackets. And then it takes a 1.0, when you put it in as 1, it takes it and converts it to 1.0 when it saves it. It just tells you that you've got a float. Resolves the conflict that might exist between a type mismatch error that might occur. So. Another built-in or primitive C++ type is the Boolean. Just to give you a little bit more information on this, we used it yesterday actually. Its only literals are true and false. Note that the type Boolean does not exist in C. It only is in C++. In C, we represent it with 0 or 1. So depending upon your compiler and what you're doing, the Boolean, I have a tendency not to use it only because I can't remember usually half the time. Am I in a C++? Am I a C compiler? Does this work? Is it false, true? Is it 0, 1? It's not supported in earlier versions. It was added later on. So use it and then experiment with it before you use it. If you have a C/C++ compiler, it works just fine. It works just fine on Dev C++ as well, so you'll never run into that problem. But if you go into like Turbo C, there's no true or false Boolean in there. It's too old for that. So Visual C++ has a Boolean though. We also have the literal constants in terms of the single quotation marks to write a literal character here. So this would be a literal character, little character, literal character. So it's non-printable characters and so we have some special characters that are represented by escape sequences. We saw those escape sequences. They're characters. They're not strings. So if we write a literal character, we use the single quotes, even though we have two characters in here. It's not a single character. It is a single character. It's an escape character because this backslash is ignored. So this is really a tab, a bell, a new line. Or then this is the one that this is a single quote. So if you want to put a single quotation mark, you do it the syntax that looks like this, which gives us the quote or the double quote. Or we've got 3 quotes in here, it can give us 2 quotes instead of 1, double quote. So usually what ends up happening is you find a situation in which, oh, how do I get a quotation mark? It's Larry's bar. How do I get that apostrophe in there? Then you have to do it this way. So, or this way. I'm sorry?
What is bell?
Oh, it rings a bell. Sound, makes a sound. Ding! Actually, it uses the sound driver that's on the motherboard. Yeah. Which is an old C way of doing things. Now people would just load on a driver and use a sound card and play music or make a sound through a sound device instead of a bell. But we do have bells on old PCs. It was called a bell, actually. Ring the bell. What do we have here? Literal constant. Generalized escape sequences are indicated by the backslashes followed by 3 digits. So if we don't like the B, is it B for bell? I don't know what it is. A for bell. We don't want to know T for tab, N for new line. We can go. We can put in the ASCII sequence for it, the digits. So that's really /N is really /14 ASCII equivalents. So those work as well if you want to use that. So those are those digits that are interpreted to correspond to the ASCII character set. So that works as well. And then we have the L for the literal constant. So the character literal can be preceded by an L, capital L, for actually it doesn't really matter, L or lowercase, to make it a literal constant, which means it can't change. It's constant. In C++, we're going to look at a keyword called constant. And constant makes it so it doesn't change. So as long as you just put the keyword constant in there, nothing in the method can change. No values are going to change. So it removes side effects. It's used for a slightly different purpose, but it's the same concept. So with this also we have what's called a wide character literal, or W character _ T, for wider character sets. So if we're not looking at standard and we want to go to Chinese or Japanese or another language character set, well, there's more digits, and there's also, or more characters I should say, but there's also special symbols and things that aren't in the standard ASCII character set. So we can create a variable that stores a character that's non-standard by using the wide character set. It just gives us a wider range in terms of what we're storing. We also have the literal string constant that's composed of zeros or more characters enclosed in double quotation marks. And here's an example here. Hello. We've actually looked at strings already in terms of the literal string constant. So this is just the terminology, but also the syntax review for you. So, and then we have the string example that can be written across multiple different lines. This is a part you may not necessarily have seen yet. So you can use a backslash as the last character on the line to indicate that the string continues to the next line. It's for concatenation by line by line. Because in fact I see this all the time. I see one line of something, and maybe it's a help screen and it's going to show a bunch of text on it or something, or put a bunch of text out on the screen. You see it all written in one line. Well, eventually you're going to run out because you have 644 characters that can fit on one line. That's it. So eventually it's going to word wrap down to 2 lines. Or people will go see out something, see out something, see out something, and put the whole paragraph like that. Well, you only have to write see out once, and at the end of each line stick one of these forward slashes on there. Or is that a backslash? I think that's a backslash. And then the backslash on there, and then it can just word wrap onto different lines and look better for you. So if you learn how to do that, then your life is a lot easier when you're starting to put really long passages of information out on the screen. So variables, what we've been looking at are called named memory storage. This is important when we start looking at pointers, which is we're going to hit pretty soon today, that are unnamed. And they call them literal because we're putting a name and then we're putting what's called an identifier on it. So when I say integer I, integer is the data type, I is the identifier, and that's a named variable. Because it's a named memory storage, we're calling it I. I could just say literal pointer I, which means reference integer pointer I, which means reference this memory space that I'm going to create in a few minutes and call it I. But we're not labeling it I, we're just going to call it that. We're going to reference it by that, which is kind of a different concept. We're going to get into that today. With a named memory storage, you read and write directly through the name. So you write to, read from, and manipulate it through the name and throughout the course of the program. Each variable has a specific type to it, which determines the size and the layout of its associated memory, and then the range of the values that can be stored, and then a set of operations that can be applied to it. And then we have variables that are also referred to as objects. When we actually did that, when we said dog space D1, dog space D2, those are also what's referred to as named memory storage. We're not allocating it as a reference, but we've named a reference to an object because objects are dynamic, which is kind of weird. So it's kind of a interesting implementation in the language, but it works. And so we can use objects just like variables, and that's how it works. So a variable here, there's 2 data values that are associated with a variable. We have the data value itself, which stores some memory. Then we have the R value, and then we have the read value, and then we have the location value. So we also have the address value that indicates the location in memory. And so where the data value is stored, this value is also referred to as the L value. No one ever says R value, L value, or anything. This is sort of the textbook part of today. So we have something equal to something. So we have the data value that's equal to a real value, the real value. If I said integer I, and I said I is equal to 12, 12 is a real value, I is the data value. The data value for I now represents 12. So generally a concept that brand new programmers need to look at. So I showed you pointers with objects yesterday. I'm going to kind of finish with that concept, and then I'm going to formally show you pointers later on today, because there's a lot more to it than what I'm showing you right now in the examples, but I'm trying to ease you into the concept because you want to use pointers. C++ programmers are the only ones who use pointers. You don't use pointers in Java. You use pointers, but you get a lot of help in Objective-C. Other languages don't support the concept of pointers either. C++ and C is the only language out there, so you may not have seen this yet unless you've programmed in C++ or C. Actually, they really come from C, but they were transferred into C++, used with objects a lot, actually. So pointer holds the memory address of another object. So I'm going to come out to dev, and let's try, this is day 1. I'm going to take day 1's example, and we're going to start in with another one. This one's going to be my pointer example. And then we're going to run through, after you've seen it one time, I'm going to apply it to objects, and we're going to see it formally with a lot more examples later on. So Actually, here, I'm going to do something else. I'm going to call this one day 2. Day 2 1. So this is going to be day 2, example number 1. For those people who came in late today, I started out the class by showing you that I put the examples from yesterday, because usually the people who come in late are the ones who aren't up to speed anyway, so otherwise you would have been here on time. Let's see, if you go into summer 2013 and you go down to object-oriented programming with C++, and you go into miscellaneous examples, you'll see from lecture number 1, source code examples. That's the one we did in the morning. And then we have lecture number 2, source code examples. That's the C++ dog and person that we did in the afternoon. So what I'm doing right now is creating lecture number 3, which is going to be the morning, and then we have lecture number 4, which is going to be the afternoon from today. So that's how the numbering is working. You don't have to send me an email message anymore. I decided I'm going to put them out here. So it was too many emails coming through, so I figured, oh, you know what, just make them available. So now they're out here. So they're also linked to the videos that I put up on YouTube as well. So I figured it was going to be too much of a hassle to keep sending it to people individually. So, all right, so now what I made here is day 2-1. So let's take a look at pointers from a non-intimidating point of view, so I can show you what I'm talking about here. Because this is kind of important. I'm going to leave these guys up here. I'm going to take, I'm going to kind of remove, I'm going to use this as a template, so I'm going to kind of remove some stuff out of here. We don't need any of this stuff anymore. Kind of go like this here. Let's just do this. Get rid of all the bunch of stuff here. There we go. Get rid of my function down here on the bottom. There we go. There we go. Alright, so what I did is I just used the example from yesterday. You can download it and use it just as a template. I'm going to leave the string in there just because I might be using a string later on. Who knows? I've got IOStream. I've got using... Oh, I didn't put using namespace in here. Did I take it out? Alright, let's do it this way. I'm a terrible typist, so I'm going to do it this way. Here we go. I'll put a get character in here. Alright, so if you like a cheat sheet kind of way of getting yourself started without having to look at a blank piece of paper and remembering what goes in there, make yourself a little template like I just did, and it looks like this. This is like the blank program, which if you go into dev and just say new project, you'll get a main that looks like this, but you'll get the whole project as well. So you can just pull the main out and save it if you wanted to and use it as a template. Alright, so for those people who were here yesterday, you know how to do integer I. So just so you know, we have integer. I'm going to go here, integer I, and I'm going to use a float f, double D, and hopefully you can get the point here, character C, that's about enough, I think. And we can put get a float, a double, a character. And I would say those are probably going to be the most commonly used variables out there. And for those people who are brand new to C, we know we can assign them by going I is equal to 10. And we can put a space in, we could not put a space in. I like to put spaces in there. You may not necessarily want to. F is going to be equal to 12.2, or whatever you want it to be equal to. D is going to be equal to 50. Oh, let's go 33.3. It's also a double value. And then C is going to be equal to, well, we have to use character, so I'm going to go here and go A. So I've got the character inside of, this is a nice little review for those people as well who need a little refresher as well. Single quotes for the A. So now I can go ahead and C out everything if I want to, and if let me just work with the I. So I like working with integers because they seem to be fairly simple for people to understand. And integers are used a lot for different things. So I'm going to start with an I and show you pointers as well as other operations that can be done. So these are called named variables. See, these are named constant variables. Why? Because we and I'm just going to document the I for everything. And this is what is referred to as a declaration. We've declared a variable integer I. So down here, this is a named, this is the named variable, this is the named constant variable, but it's referred to as an assignment or an initialization. The first time we give a value to the variable after we declare it, it's really referred to as an initialization, but isn't it also an assignment? So technically this is an initialization because we've initialized the variable and have given it a value. If I said, after the first one, if I said I is equal to, let's change it to 20 now, this is also an assignment. This is an assignment expression because we've assigned a value. What, isn't that also an initialization? Yeah. So the two words are sort of used interchangeably, but the first time you declare it, you need to initialize it normally. So I can come up here and give another integer and say integer b, integer another equals 0. So this, actually, here, let's just do it this way. Integer II. This is another declaration, but also an assignment or initialization. Initialization. All in one. Assignment, declaration and initialization together. So don't get tripped up on the words. That's what it's basically trying to say. So if I compile, make sure I'm good, my syntax is good, I'm ready to go. If we're not comfortable at this point, there's nothing really I can do for you. Get a Deedle and Deedle book, unfortunately, because this is a graduate level course. I can't go back and teach you undergrad CS concepts. So, going forward, I'm not assuming that you understand pointers because you may not have seen this unless you've seen C++ before. So we have this guy here, it's called integer I, and we know we haven't used any special symbols or anything. This is what we're familiar with so far. So I'm going to make another integer declaration for another variable I'm going to use, but I'm going to call it a reference. I reference it with a special symbol called an asterisk. So I'm going to go integer, and I'm going to use this asterisk, which is Shift 8 on my keyboard, and I'm going to call it PTR for pointer. So this is a reference variable. So this one up here is a named constant variable. But nobody says named constant, they just call it a variable. It's okay. You can call it anything you want. This is what's called a reference. So the keyword here is reference variable. So I'm creating a reference to a variable. What does that mean? I still give it a data type. I still use it as an integer, but I'm not naming it PTR. So in order for me to use this, I actually have to create an integer to use it with, or assign it to another integer I've used it with. So we have this other thing called the address of operator. So this is, so let me make a little note here because this is for teaching purposes. I'm going to go here. I'm going to go, in this context, the asterisk is called a reference. Reference symbol. It's a reference symbol. It's also used as a dereference symbol. And then we have another symbol, the ampersand, that's used as an addressive symbol. So if I wanted to use PTR now I can just go like this. I can say PTR, but I can't do this. PTR equals 10. That is wrong. It's wrong because it wants a memory address. So references refer to memory addresses. Named constants refer to values. which is why I showed you that lecture to start out with, to show you that it's a literal, this is a literal constant. It's equal to a value, an R value or R value is equal to the L value, right in the left part of the thing. Whereby this is technically wrong, unless we know memory address 10, but we don't get memory addresses. We don't have privilege in the language to know what memory addresses anything is attached to. So when we do this, we've already started down the wrong path, because this isn't a name constant, it's a reference. So it wants to be equal to a variable. So we can use the address of operator in this case. So I'm going to write PTR, and I'm not using a symbol. I'm using the name of the variable. So a lot of people can make the mistake and go, every time I do this, I have to. It's not actually called asterisk PTR. It's called PTR. That's the name of the reference. So don't put the asterisk unless you want to dereference it. I'll show you that in a few minutes. But PTR is not going to be equal to. If I wanted it to be equal to something that's valid, I can say, what about the address of I? We got I up here, and we changed I to 20. Now I is equal to 20. So I'm going to go, okay, so then I'm going to go the address of I. This is legal since this symbol here means, and it literally means address of. So the address of I, so PTR is now going to be equal to the address of I. So let's print some stuff out to the screen so we can kind of see what we're looking at. So if I print out I up here is going to be equal to 20. Actually, let's just go here. Let's just say I is equal to 200. We can change the value of I all we want, but right here we can see it's equal to 200. And we know that PTR is equal to the address of I. So PTR should also be equal to 200. So let's test it out. So we go cout, and we're going to go here, I is equal to I. I'm waking up too. Alright, so then we have cout PTR is equal to, I know I'm going to get an address when I do this for those people who know what I'm doing, but I want to show you something first. PTR, it's going to give me, it's going to print out an address. Oops, end line. Enough typing for me. So I'm going to print out I right now. I'm going to print out PTR. That's really going to give me a message. That won't actually. PTR, because we have two of the variables here. We have PTR up here. Let me move this over this way so it doesn't look as confusing. Take out this line. There we go. We have this guy here, and we have this guy here. If I want to print out I, I'm going to get whatever value is stored for I. When I want to print out PTR, I'm going to get the address of I. Is it going to be of any meaning to me? No, it's going to look like a bunch of hexadecimal characters. So it's going to look like this, actually. I got I is equal to 200, if you can see that on your screen there. I'm going to make it a little bit bigger here. There we go. And you should get something that looks like a hexadecimal number. It's really the memory address that PTR is holding on to. I'm going to have that memory address whether or not I've assigned it to anything. So let me go backwards a little bit here. And I'm going to comment out this assignment expression here. So now I've just created PTR. It's not equal to anything. I just created this reference variable called PTR, and I haven't assigned it anything. Well, if I compile it and I run it, I see I got a different, well, you didn't look, I didn't write down the address, but this is a different address than we saw a few minutes ago. Because this is nothing. This is just a generic old address it's pointing to. Well, it's not anything, really. It's just a memory address. Makes no sense. We can't use that in the code. We can't say, okay, go to that memory address. If we wanted to go to that memory address, we dereference the memory address by following the pointer to that memory address, which I'm going to see in a few minutes. Let's do the same thing with I so you can see what's going on here. So we have I. Here we have I. Let's take these guys out. Here, I'm just going to comment them out actually because I put all those lovely little codes in there. I haven't assigned anything to I yet. I just said integer I. I have integer I right up here. And then down here I've got integer PTR. So now I've taken away all the assignments for I and I'm going to print out I. Well, what's going to happen with that? Probably going to get garbage now. Oh, now I got 2. Where'd 2 come from? It's garbage. It doesn't mean anything because I haven't assigned it anything. It's actually the garbage that was left over because the last time I used I a few minutes ago, I assigned it to 200 because, you know, that's what was there. If I shut my computer off, turn my computer back on, run this again, I'm going to get like some other number. It's garbage. It doesn't mean anything because I didn't put anything there. However, I can show you that the address of I and pointer I are going to be pointing to the same thing. So let's put this back here and make I now equal to 200. If I run it now, I'm going to get the 200 that I expected because I've actually given it a value. So now I have the 200. And I have PTR is equal to 3D2430. So now let's make PTR equal to the address of I. So now we're going to see, I think I said 3D something. It started out 3D something. If I remember this right. Now I've got OX22. A few minutes ago it started out 3D. So make a mental note of this one. This is actually easy to remember. This is the address of I. So if I printed out the address of I should see the same thing. So PTR is now equal to OX22FF. I'm just 74. I can probably remember that with my temporary memory. Here, we'll see. I don't have to write it down, I don't think. In a few minutes I'm going to see them both together, I hope. So I'm going to print out the address of I equals. If I wanted to do that, well then I'm going to print out this ampersand symbol along with I because I want to see what the address of I is going to be equal to. So I'm going to put in here address of I. And if I print out what the address of I is, PTR is going to be equal to the same thing because I just assigned it to the same thing. So I'm going to run it this way. And lo and behold, it is the same address. So PTR is equal to OX22FF74. Well, lo and behold, well, the address of I is also OX22FF74. If I wanted to make it clear, what I should have done actually was this here. In fact, I'll change this just so when people who aren't here today are looking at this example later on. The address of I, PTR is equal to the address of I, so we have the same kind of behavior going on. It's just shorter so you can see it closer together. And that's what really the address of I. When we say PTR is equal to the address of I, we're making it equal to it. So I can go ahead and now change PTR, or I can change I. And they're both pointing to the same address in memory, which is why we're using a pointer. We don't have multiple copies of it, we just have one. One piece of memory that was allocated. We called it I when we created it. We created it as a name constant in this particular case. So now I'm going to go over here and I'm going to change I. Now I'm going to say I is now equal to 4. No, let's make I equal now to 777. We'll give I a lucky number here. 777. And then I'm going to cut and paste this here. Copy it. Paste it down here. And I'm going to change it a little bit now. So, actually, before I do this here, let me cut this a little bit. I'm going to cut this out here a second. I want to print out what would happen if I followed PTR and got the value. So we know that I is going to be equal, there's a piece missing here. If I is going to be equal to I, here, and we're going to print that out, I also want to print out, well, what is PTR equal to? We know that PTR equals to the memory address of I because we assigned it right here, actually. What if we want the value that's stored at I? We can also get that. But what we do is we dereference at this point. So I'm going to put in here follow I, oops, follow PTR equals, I'll explain that in a few minutes. Well, then let's just follow PTR. So this, in this context, follow PTR, the asterisk is a dereference. Dereference. There we go. So in this context, when we say follow PTR, so I purposely say, and I've actually unfortunately got into the bad habit of doing this, when I go integer reference PTR, so when I see it in this context, and if you notice, hopefully I'll be consistent, I say integer reference PTR, follow PTR. So when you see it in this context without a declaration, it's always a follow, which is a dereference. This is, when you see this symbol, always say to yourself, the address of I. So ampersand means the address of, so substitute the words address of if you're saying this in English. And this is follow PTR. Well, if I follow PTR, PTR is going to be equal to the address of I, so whatever I is, PTR should also be equal to that. And if I'm following PTR and PTR is equal to the address of I, then follow PTR, I'm going to get, well, in this case, I'm going to get 200. So I should see 200 printed to the screen for the follow PTR. So, unless I have a mistake. Huh? Yes, I can. Let me repeat it one more time. No, I've repeated it all day today, but let me repeat it one more time. When I see the symbol up here, let me start from the beginning. The definition of a reference. So here's everything you ever needed to know about. This is the entire concept of pointers, by the way. A pointer is a referenced variable. When you see the asterisk used in this context, instead of saying integer I, I'm saying integer reference PTR. I can also call it I. Well, I can't call it I already have I. I have I as a non-reference. So I'm using PTR. I could use P. Doesn't really need it, whatever I want to call is whatever I want to call it. So in this context, this asterisk is called a reference. So integer reference PTR. When I say PTR is equal to something, PTR is going to be equal to the ampersand I. Well, the ampersand in this context, if I were saying it in English, is the address of I. So reference, I'm going to have a reference pointer, PTR, reference, address of. In this context, because I'm not making a declaration of it, and I'm not initializing it, I'm not doing anything. In fact, the initialization, I'm just using it as PTR, because PTR is holding a memory address. PTR wants to hold a memory address. It doesn't want to hold a value. It holds a memory address of a piece of data that holds a value in this particular context. Here, the asterisk means follow. So here it means reference, here it means follow. What is follow? Follow is really a dereference. So it's like, reference me and then don't reference me. But people like I think people can understand follow a lot easier from the way I learned it. They never called it a dereference, they always called it a follow. What do you mean follow? Follow the memory address and give me what's on the memory address. Instead of giving me the memory address, follow the memory address and give me what's at the memory address. Well, in this particular case, if I followed it, the memory address that I've given and I've assigned to PTR is the memory address of I. So now I have I and I have PTR pointing to the same memory address. If I change the value that's at the memory address through I or through PTR, it's going to be the same value for both. So if I run this here, so now I have I. This is the part that's going to be interesting, actually. We don't necessarily need to deal with the memory addresses anymore, but I'll leave them on there just anyway. And further down, next time I do it, I'll take them off. If we have I, we can see what I is equal to. If we follow PTR, well, it should be equal to the same thing that I is equal to. So these two values should be the same thing. So if I run it, let me make sure I compiled it. There we go. And make it bigger so you can see it. There you go. I is equal to 200. Follow PTR. Well, lo and behold, it's also equal to 200 because it's equal to the memory address of I. And I is equal to 200. They're both still at the same memory address. We can see it right here. Let's take it one more step further. Well, let's make another one. So I can make a dozen of these suckers, actually. So now I'm going to comment this line of code out here because you guys know they're at the same memory address, right? Hopefully. I'll leave it in the code, though, because I'm going to leave it in this example, because I'm going to give you this example at the end so you can have this, you can play around with it and see what's going on. In fact, we don't need this side piece here anymore either. Make it a little bit bigger. There we go. Let's make another pointer. We can declare variables anywhere we want in here. So I'm going to make another one. So I'm going to go I'm going to say integer. When I define a piece of data, I always have to give it a data type. And I'm using integers now. In a few minutes, I'll use a character, or I'll use a float. It can be done with anything. It doesn't have to be just integer. So I'm going to declare a new pointer. So I'm going to go integer reference, because I put this asterisk in there to say now I'm referencing something. I'm going to call this one PTR2. So I can also declare and reference all in the same spot, just like I said integer I, and then the next line underneath I said I is equal to 0 or I is equal to 100. Well, I can also go integer pointer, reference PTR. You can say pointer PTR or reference PTR. Well, that one's going to also be equal to the address of I. We're going to really use I here. The address of I. Now then, if I wanted to, well then I can just see that if I print this out here, this is now PTR2. If I followed PTR2 and I printed out what was at PTR2, following PTR2, I should also get 200 because I is still 200. Now I have three things pointing to the same memory address. I got I is equal to 200. I got follow PTR is equal to 200. Follow PTR2 got to be equal to 200. So now I got three references to the same memory address. If I printed out the same memory address for all of them, if I printed memory address out for all of them, they all be the same. Yes?
Percent I is equal to address of I or it's a value of
I is a regular old variable that we created. And I represents by the named constant. So this is why I wanted to kind of give you the vocabulary for it. A named constant is an identifier for a memory address. I actually represents that x22ff74 something or other address, but we never see that address. Instead, when we use I in this context, we say I is equal to 200. It automatically puts the value 200 into the named constant identifier I. I represents OX22 something or other. If I want the address of that, instead of 200, I want the address, I use the ampersand. The ampersand in front of I, in this context here, if I said that PTR is equal to, let me show you something else here. If I leave out the ampersand and have it equal to I, then it's going to be equal to the memory address O something or other. If I followed PTR, let's do it this way. I'm going to follow PTR, have it equal to I, not, no, that's going to be, if I follow PTR and have it equal to I, it's going to be equal to 200, because I represents 200. So if I follow PTR and had it equal to the ampersand I, then it's going to be equal to O.OX22FF something or other. So the ampersand is giving me the address of any variable. You can use it with a float, a double, a character. It's just the memory location where I is in memory. So I use the memory location and I assign it to PTR. In this context, I don't follow PTR because I want PTR to point to that memory location. If I followed PTR and had it equal to the memory location, if I put this in here, now the value of PTR is not equal to 200, it's equal to OX something or other. If I print it out here, let's just do it this way. Oops, I'm going to get a message here. I can't do it. Oh, I have to take this out. This is legal since this is not legal. I made it illegal. We don't want to follow PTR and have it equal to the memory address. It's not going to work.
So address of the
It's a circular. What do you call it? It's not a good assignment. We're going to get an error message because this wants to hold a memory address. We can't have it hold a memory address and a value because that's not an integer value.
Reference and address can't be divided.
The address is not an integer, so that's why I got the message. In fact, actually, I can probably, well, it's probably still here. Invalid conversion from int to int, because PTR is supposed to be holding an integer. I can't have PTR hold a memory address because that X, it's a hexadecimal representation. It's not an integer representation. If I converted it, well, here's if I wanted to make it work. I typecast this to int. Really bad idea because you're never going to use it for anything. This might actually work. And let's see. Yeah, so if I do that, I don't know what typecast integer value I'm going to get out of there. Oh, here it is here. It's 229. If I converted that hexadecimal into an integer value, I end up with this value, which makes no sense to me. But it can't store. It can't store the integer value. I mean, it can store the integer value. We don't usually work with the addresses. We don't need the address for anything. Instead, we use the address through the reference. We reference the address through the pointer variable. So, good question. I encourage you to ask questions because now is this is like the most important part of this weekend. Because if you don't understand pointers, you're not going to understand them with objects. You're not going to understand them with linked lists, with tree structures, with anything really. So, but don't worry if you don't understand them completely right now. Just work with me. We have a lot more lecture stuff on pointers as we go through. But so, but this is like this is the foundational material that really hopefully puts the pieces together for you. And it's all being recorded so you can watch it over and over again. So, all right. So back at the ranch here, we have We got a new one here. We got PTR2, and hopefully I fixed this one here. Yes, I did. Okay, good. Now PTR2 is also equal to 200 because it's also equal to the address of. So if we changed I at this point, so I has always been equal to 200, and we now have this new one here, and it's also equal to the address of I. So let's flip things up a little bit. Let's change I and make I is now equal to 777. Now if I is equal to 777, now I can make my life easier here by cutting and pasting here. Paste, and take this guy out here and copy, paste it here, paste it here. And I'm going to put a little guy in here so you guys know what's going on here. I got, well, let's just go here. I changed to 777. So now that I is changed to 777, I is now equal to 777, PTR is going to be equal to 777, PTR2 is going to be equal to 777. They all changed because we changed it someplace. So, because I got changed, everybody else got changed too. So now we're all equal to 777. So what if this guy over here decides, well, I want to change I. I'm pointing to 77. I'm pointing to I. So, okay, you can change him. If we're going to change him, then we're going to follow the pointer, have it equal to 888. So we're going to follow PTR2. So instead of printing out after I followed PTR2, it's equal to 777. So now if I follow PTR2 and have it equal to 888, then actually I don't really need to, let me put a C out here at the end. I'm building all my examples here. End line. You know what, let's just put 2 end lines at the end here. Get smart about this. End line, there we go. Now if I cut and paste this piece, and I'm going to print them all out again. Paste. 888, and this was really follow PTR2. So PTR2, following PTR2, changed to 888. It's going to change for I, it's going to change for PTR, it's also going to change for PTR2, but let's just go here. Oops. It changed for everybody. So we have PTR2 changed for 888, I, 888. Oh, look at that, it changed for everybody. Because now we only have one piece of memory we're working with, the address I took out of there, but the address is on the top there somewhere. It was the OX22 something or other. If we reboot the computer, it's going to be something else. It always changes. Whatever the runtime environment decides to put this I that we created is going to be the memory address that's going to be used by all these other pointers that are all pointing to the same memory address. So instead of allocating in this particular case, I have 3 variables. I could have allocated 3 different memory locations, all for the same value that I'm manipulating through the same reference. Oh, excuse me, different references, all to the same memory location. What does that allow me to do? Well, it allows me to only make one object, put it out there, and then reference it by other objects. So we only have one piece of memory. What are we doing? We're sharing a piece of memory between all of these different objects, all these different pointers to the objects, which allows us to be more flexible in the use of the memory. And we're going to see later on it allows us to do other things with it as well. If we allocate it, then we can deallocate it. And we can use it different ways. But we can also create 2 commonly known problems. One is a memory leak, the other one is an inaccessible object, which causes a memory leak. And then we also have a dangling pointer. Let me show you what a dangling pointer looks like, actually. Well, actually, before we do that, let me show you a memory leak first. So we should be good at this, or we're not good at this point, or we have good. Good time for questions before I move forward. Yeah.
Got the same value of as ATP that start PTR2 because start PTR is a reference of.
PTR2 is equal to the address of I. Well, PTR1 over here, or PTR, is also equal to the address of I here. We made them all equal to the address of I.
You have changed the value.
What did the value of I change to 888?
Because we followed PTR2 that was equal to the address of I, and we changed it through this reference to I. We referenced I from another variable, and we changed what was located at the memory address that was assigned to I. So I got changed. Everybody who references that. Imagine out here, actually, maybe I have a paint program here. This is what's going on here. Let's see if I can do this in paint. Let's see. Let's see my writing skills here. Make this a little bit bigger. Let's see. All right. Let's just do it this way so I can move it around. Here we go. See, normally I like a board, but this works. This works. When I say, wait a minute here. Let's do it this way. Integer. Why is it caps? Cap lock. All right, imagine this is a lowercase integer I. I'm stuck on caps for some reason here. And that, here, actually, that's bad. I said integer I. All right, let's just do it this way. I got a better idea. This is the memory address. When we say integer I, imagine I wrote integer I up here. And I put in a, if I were doing this on a chalkboard, I'd draw a little arrow and say, this is the memory address. And the memory address, I'd write the memory address above it. And the memory address above it would be like 2222, whatever that memory address was. And this is the hexadecimal address of what was created. And from integer I, in here, I'll just do it this way. This is integer I. Imagine this is a lowercase. You know what? Maybe I can just do this here. Maybe it's because it's in the... Ah, look at that. I got it. Integer I. There we go. And if I said I is equal to 200 in my example here, then I come over here and I got 200. And I probably should have stuck this outside because this is really the memory. Let's just do this for a second here. Imagine this got messed up, but don't worry about that. Out here I've got a memory address. The memory address is 222. I said I is equal to 200. I put 200 out here. If I said integer p and I made it into a pointer, I don't get this 2222. I don't get anything. So this guy gives me this. There we go. This guy gives me nothing. I don't get anything because I created a reference with this guy here. So this thing told me it was a reference. I don't get anything. I don't get 200. When I do this though, this is when I get p is equal to the address of I. All of a sudden then I get this. Oh, yes, you're right. You're right. Well, it is the address, but yeah. It is the address, but it's pointing to the same address. I'm going to leave it right here, actually, because what I'm going to do down here is I'm going to say, if I'm referencing it through P, if I say follow P and have it equal to 10, I thought it was going to work. Let's just go this way. My space was bad. There we go. 10. Then I'm doing this. I'm following, here, let's take this guy. Let's do it this way. It's primitive. Let's see. There we go. I feel handicapped. So wait a minute. Okay, got it. Let's do this one like this. And then we'll go like this. And then we'll go like this. That does this. So now if I see out I is now 10. Anything that's pointing to I is always going to be the value that's stored here. So this is the value that's stored at the memory address. These guys are just pointing to the memory addresses. This ampersand says give me the memory address. So I'm pointing to the same memory location. When I reference it, if I go here and I go back like this and say, oh wait a minute, I don't like that. I don't like what you did there. I'm going to go I is now equal to 50. If I do that, I've done this. I've taken it back up here again and said, okay, no more 10. now I is equal to 50. Let's stick 50 in there now. And then now if I follow PTR and print it out, it's equal to 50. Or if I follow PTR, I'm going to remove 50 and I'm going to change it to something else. So we're all accessing, all these guys are accessing the same memory address at the same time through different operations. So we only have one little piece of memory. The flip side of that is, can we do a new one here? Here, let's see, maybe I can make this a little bit bigger. Here we go. If I did this, I go integer A, B, C. I get this. I get A, oops, B, C. This is a 100, 101, 102. I get 3 different memory addresses instead, with 3 different allocated, so these are the memory addresses, let's say. So I get 3 different memory addresses with 3 different allocations. This is going to take up more memory on my program that's running. This is going to take up less memory. What if this was like a list of items? Then I keep having to change everything here. So this is, I know it's way too early to bring this concept up, but this is a linked list. I mean, it could be a linked list. If we have allocated 3 items, and we have this order that we set this in, and the order that we set it in was A, B, C. And then we have, oops, hold on. A, because we're calling it A, B, C, and it's at memory address 100, 101, 102. If these aren't named and these are just references, then we can switch the order around. We can go like this. B, BAC, or whatever. I can switch the order of these guys without moving anything around. I just change the references to the memory without picking this up, moving it over here, picking this up. Why do we need to move this around? We don't need to move this around. The original ABC can stay here, and I can switch these two without having to juggle like in an array where you have to take what's in 0, put it in 1, what's in 1, put it in 2, or put it in 0. You have to go back and forth, but I haven't looked at arrays yet, so we're going to do arrays today too before lunch. Yeah? Well, these would be pointers, and so if I made this as a reference, I'd say, well, if I have a list and the list is 1, 2, 3, let's just do it this way. If this is if I had a list here, I can order the list in any order by moving around which address is going to be stored to which one. So let me just finish it off this way. I'll just go like this. I go 1, 2, 3. Well, let's just, we only have 3 items. This is my list, and 1 could be pointing to here, 2 could be pointing to here, 3 could be pointing to here, or something. Instead of moving this all around, getting rid of it, creating more of it, it's a more efficient use. We're not going to hit linked lists until the 3rd weekend session, but that's one of the uses of a pointer system and reference system is it's more efficient to just create a bunch of references to the memory and move these references around. Because I can do this. I can come back out here and I can say, well, PTR2 is equal to PTR1 or PTR. That's a valid expression. And if just one pointer is not equal to the other pointer, and so that I switched them, or actually I assigned this one to this one. In this particular case, we haven't caused any problem because I existed and we can reference I. If I had said, in a few minutes I'm going to demonstrate a couple problems, but if I said PTR2 is equal to new memory, a new integer, and then I got rid of that and I said, well, PTR2 is now equal to PTR, what happened to PTR memory that was allocated? It's inaccessible. It's gone. There's no reference to it. So let me show you something else actually. Now that I'm looking at this, I'm going to make this a little bit bigger here. We have a way of, what I've been showing you right now is how to access through a named constant. And we've been naming it, what's wrong with this guy? Oh well. We've been naming it I, and we've been using the address of I for everything. So I can take and use the new operator and create a brand new piece of memory. And when I use new, I'm going to show you that in a few minutes, we do this. So if I go new int, I say give me a new int, I get this that has a memory address on it, and so let's just call this one 103 just to be consistent with our memory. I got this guy. Usually I'm going to go, one of these guys is going to be equal to new int. So if I do this, I can go following down here on the bottom here. P, what I have, I can go P, which is a reference, is going to be equal to new int. Oops, I'll stretch it up this way. Semicolon. If I do this, I get this. I get this new int that showed up over here. This is my new int over here. When I do new int, this is a new operator, it says create me an integer. I didn't put a name on it. It's the equivalent to saying integer I. But I is the name, the identifier that I'm putting on the memory space. Integer I gives me this. And we have I. This is where the I comes into place. The name of the identifier. We got a little label up here. It said, oh, I'm I. And I said, well, if I said, well, P is going to be the address of I, we have I, we're labeling I. When we go new is a keyword added to, well, it's a C++ that says create a new int, but don't put don't put a name on it. So it's a nameless new piece of memory that I allocated over here. Now I can follow P and have it equal to 10, and 10 gets put in here. Follow P, have it equal to something. This method called newInt returns a memory address. So now P is going to be equal to 103. This here returns a memory address. P is now equal to 222 because we took the address of I. So P is equal to 222. Now here P is going to be equal to, technically, if we were to look behind the scenes, P is equal to 103. Because of this operation here. So P is equal to 103. So if I followed P and had it equal to 5, so I follow P, have it equal to 5, then I've done this. Whatever was there is now equal to 5. It's no longer new int. So new int doesn't get put there. I just put new int on there to show you what happens here. Now I can't say, and people have tried to do this, I can't follow I. I is not a pointer. Integer I is just an integer. I is over here. I can't follow I. I is the name of the variable that I did a new int with. But instead of saying, you know, pointer I is equal to new int, I said integer I, which is the shortcut way of doing both of those two operations together. But then I created a named variable, and I called it I, instead of in this particular case where I just said new int. There's no I on here, and there's nothing on here. So then if I do this, I'm going to create a couple problems. I'm going to demonstrate these problems in a few minutes. If I do this, and, oops, I need a, if I do this, well then P is going to be equal to a new int. Or actually, here, let's just go P is equal to the address of I. Let's just do that one. Well, then I've done this. I've done, at this particular point, now if I say P is equal to the address of I, I've removed this linkage here. And now I have this new linkage that I created with this address of I, and I'm up here now. Oh, here, let's just do it over here. Now I'm back up here again. Who's linking to this? Nobody. I created a piece of garbage. It's called a memory leak because I allocated and I didn't remove it. I didn't take it out, and then now nothing's pointing to it anymore. Nothing's pointing to it anymore. It's inaccessible. inaccessible objects are wasted memory. There's no garbage collection. So what garbage collection does in languages, it goes around and a garbage collector would pick this up. You say, hey, wait a minute, no one's pointing to you anymore. You have no reference. It's called reference counting. So maybe Objective-C will make more sense to you now. Automatic reference counting keeps track of P's and I's and everybody, and who's pointing to who and who's using which memory. And if I have a reference pointing to this, and reference counter keeps track of it, and it's usually an on or an off. Yes, somebody's pointing to you. Okay, good. If someone's pointing to me, I must be used. If I'm being used, then I'm going to stay. Nobody's pointing to me, the reference count is 0. Nobody's pointing to me at all, you're garbage, which means remove you out of memory. So in C++, nothing's automatic. There's no automatic reference counting. There's no garbage collection. There's nothing. Not like Objective-C. So in C++, you have to do this. If I'm going to do this, before I do this, I'm going to write this one here. I'm going to go delete P. If I do delete P, before I do, if I do delete P, I want to do delete P up here. I got more lecture stuff I'm going to show you on this actually. Let's just do it over here. Let's not worry about the order that we're doing stuff right now. If we delete the P, this guy goes out here, says, well, what's P pointing to? Because P's a pointer. P is equal to new int. So here, I know what I'll do is I'll send it. I'll put it over here. We don't have the 5 anymore. I'll put the guy here. This guy was follow pi. I have it equal to 5. The delete P operation is going to do this. It's going to come over here and do this. Get rid of it. So we don't have any inaccessible, but we have to delete it through the pointer. So in order to get to the memory, we have to reference it. So to reference it, we have to, to delete it, we have to follow the reference and delete what the reference is pointing to, which is how we go. We delete through the reference. So we delete P, but P is still around. Because P is just a reference. Whatever P, well, what is P? In this particular case, P is equal to 103. So we're deleting 103. Are we deleting P? Nope, P is still around. So I can go P now. In this particular case, I can say, well, P is equal to the address of I. And now I've removed P, and P is equal to the address of I, and I've reassigned P to the address of I. So now P is pointing to something. Otherwise, I'd say, well, P is equal to null. And then now I know that P is not pointing to something. When I do this, without doing this, I've created what's called a dangling pointer. Because I have P pointing to something now that doesn't exist anymore because I just deleted it. So now if I go follow P, I'm going to get garbage. So then I go, well, P is equal to null. What I'm saying is this here. I'm saying P is equal to null. What does that mean? It says, well, P's not pointing anything valid anymore. If it's not pointing anything valid, we're not going to follow it and get something that's been deleted. So usually you see these, and I'm going to have some examples for you. Maybe we should take a short bio break soon. But if we do that, then P is not pointing to anything that's illegal. It's pointing to nothing. And we know if you follow P, we're going, you know what? P is equal to null. Don't follow P. Okay. But we can reassign P. We can go P is equal, then this is going to be the next line that we're going to do. We're going to go P is equal to the address of something. Or P is equal to new int. We can do that. We can do this operation all over again. Because now we can create something brand new if we want to. Well, why are we going to create something brand new? So usually we're not going to delete it, create something new, delete it, create something new. It's wasteful in terms of efficiency. You want a program to run fast, you allocate just the memory you need. You keep changing the pointers to the memory so that you can manipulate whatever value is at that memory address anytime you want. So, time for a short bio break or no? Are we good? Those people who have been there at 9, it's a 9, 10, it's been an hour and a half. So, bio break. Yeah? I'll leave it here. I'm not going to do anything with it. So, let's take a short bio break. We'll come back with part 2 of this. I have more stuff to show you on pointers, so don't worry about it. So, absorb, take a bio. Actually, I'll pause this video so it's all together. I am going to break this out into a separate part. So this one here will be stored as an image file, and I'll attach it to the video, because what I'm going to do in the next part is run through the source code for this, and I'm probably going to want to write up a new, I'm thinking ahead, I'm probably going to want to write up a new visual for it. So I'm going to end this. This is for my YouTube people. I'm going to end this video and start it fresh with another section that's going to be a continuation of this. So.